Hello everybody, it's Mr. Ray with our next lesson in grade 12 data management. Today we're working in unit 5. We've started the unit talking about continuous variable distributions, and we then proceeded with the last lesson where we introduced the normal distribution, which is an example, the most famous example of a continuous variable distribution, and we learned a lot about how you can use z-score tables to actually predict values between two different measurements. You can predict the percentage of time it will happen between those two, the range of variables. So we're going to continue on a bit. This lesson won't be quite as dramatic as the last one. We're going to continue working with what we've learned in the last lesson, but just add a slight new twist to it. So what we're going to be introducing today is two things. We're going to talk about how we could take a sample of a population that is normally distributed, and we can actually assume to a certain degree that the sample of any normally distributed population, the sample will be distributed normally as well. Okay, so there's a few assumptions here. Basically, what I just said about how you can assume that the sample mean and the sample standard deviation are estimates of the population mean and population standard deviation. And here's some common sense here. Basically, the larger the sample is, the more reliable the sample data will reflect the population, and therefore how much closer the mean and the standard deviation will be compared to the population. So the other thing is the main part of what we're doing here, and we call this method the continuity correction. And what this is, based on the definition here, it's a method used to adapt discrete data. Remember, discrete data is just looking at things that can only be integers, to the continuous data used by the normal distribution model and calculation methods. So what does that mean? Okay, so I've kind of expanded it a bit here. Discrete data can sometimes be modeled by a normal distribution. You might be told that something that is measured in integers is normally distributed, which is fine. But what do you do when you're working with single values? Like, for example, so just let me finish this. Continuity correction should be used to calculate probabilities with these models. That's what we're going to learn. This is done by setting an interval for a particular integer value. So instead of testing it is the variable equal to a certain value, we can't do that with the normal distribution. Remember, on the z-score tables, you have to basically find the probability between two values. So what do you do if you just want to see if it's equal to an integer? And I talked about this in the first lesson, and basically said that you can't really test for a single value, and that is still true. But what we do is we do an approximation, a correction. Okay, so for example, if you wanted to test if a random variable is equal to 7, x equals 7, well, you can't do that. You can't test as the probability of x equals 7. That doesn't work with a normal distribution. What we do, though, since the only values you can have here are integers like 6, 7, 8, 9, etc. What we do is we set up a kind of a fake interval where we go plus or minus 0.5 on either side of that integer. So if we really wanted to test the probability of the random variable equal to 7, we would actually test the probability that the random variable was greater than 6.5 and less than 7.5, and that would capture basically plus or minus around 7. Okay, so what you're kind of doing is you're dividing up that decimal region between 6 and 7 and 7 and 8, you're splitting it down the middle and say, okay, 7 you can have from 6.5 to 7, and from 7 to 7.5. If I was testing for, say, 8, I would test from 7.5 to 8.5. Okay, so it's kind of a neat little correction that allows us to use the normal distribution for discrete data as well. Okay, now the first example here, we're kind of looking at investment returns. So this is a sample of investment returns, and we're just going to show how we can use a collection of sample data, and we can actually assume that it's distributed normally as well if the population data was also. Okay, so it says here the annual returns from a particular mutual fund are believed to be normally distributed. Okay, so this isn't just the last 5 or 10 years. This is for the history of this mutual fund. So the entire population of years where we've had this mutual fund. Erin is considering investing in this mutual fund. She obtained a sample of 20 years of historic returns, which are listed in the tables below. So I'm not sure if that's the last 20 years or just random 20 years of the history of that fund, but it's still a sample. So we're going to be asked, notice they didn't tell us anything about the mean or the standard deviation, which is what we would need to use if we're going to work with probabilities of that rate of return being a certain value. So the first question is asking what's the mean and the standard deviation of this data, which is a sample. So what I would do first is not really interested in the years, that's just kind of an index, but we are interested in all these 20 returns. The order doesn't really matter, this is just a collection. So if I look at just those, you can see, well, we knew it was 20 years, so it's 20 pieces of data, 20 samples. And if we add up all the values, if we call the return value x, the sum of all the x's is 246.7. So I obviously did that in my head, not really. Did it before the lesson. So now we're going to actually need to know this when we do our mean and standard deviation for this sample. So since it is a sample, we're going to use the correct terminology for mean, which is x bar. So x bar is equal to the sum of the x values divided by n. Well, luckily we just figured what those are. That is 246.7 divided by 20, and that works out to be 12.435. Now you can see the actual units for these numbers are percent. So if you want to get official, you could put a percent sign there. I'm just going to leave it for now, but you can assume the units are percent. Now the S value, which is the standard deviation for a sample, we're going to use, I introduced this in the last lesson, this kind of fast estimated version of, instead of having to do that table we did last unit, this formula is square root of x squared minus n times x bar squared all over, and this is where you have to remember this is a sample, so it's n minus 1. Okay, and I guess, yeah, I'm not going to bother with this in terms of the individual values. I'm just going to go right to the final answer. It's 9.49. Okay, you could check my math if you'd like, but that's what it is. So we've got the mean and standard deviation. This is going to allow us to use the normal distribution and z-scores to answer any questions about probability of a certain rate of return or return below a number, etc. So we've got a couple of those questions here. Assuming the data are normally distributed, which is I mean, that's a fairly safe assumption, but they've kind of made it for us. What's the probability that annual return will be? And the first part is at least 9%. Okay, so the first thing I'm going to do before I start working with probabilities is look at my random variable, and that's going to be x as usual, and that's going to be the rate of return. And like I've said several times before, you can't, and that's in percent, you can't just start using probability x is greater than something without defining what x is. So this will apply to all the remaining questions here because they're all going to be about rate of returns. So this is at least 9%, and the units are already in percent, so I don't have to change it to 0.09, it's just 9. So we're looking at the probability of x, the rate of return, at least, so greater than or equal to 9. And if you remember my examples from the last lesson, this equal sign doesn't really have an impact. So if it says at least, that is greater than or equal to, but if the question had changed to more than 9%, and I put a greater than sign there, it doesn't make any difference at all in the calculation. So, you know, you could either put it there or not, it doesn't matter. Okay, that's going to be equal to, now I need to change my random variable. The value of the random variable is 9. I need to change that into a z-score. So if you remember, over here we'll do the z-score calculation. And the formula for that, I'll just put it for the first one, is x minus x bar over s. And we've just got our x bar and our s from here. The x value is what we're looking at here. So for our particular case, it's going to be x is 9, x bar is 12.435, and s is 9.49. And if we just do that calculation, we get z is equal to negative 0.36. So this part should seem very familiar from the last lesson. In fact, this probably too, even though I believe we just did population mean and standard deviation, but you know how to do that from the previous unit, I hope. So now what we do is we change the probability based on x into a probability based on a z-score. So all I do is I change the x to a z, and I change the variable x value to its associated z-score. So greater than negative 0.36. Okay, now the problem, and we talked about this quite a bit last lesson. The z-score table only gives you values, percentage values of z being less than a number. So anytime you see a greater than, you have to do the 1 minus trick here. So it's going to be 1 minus, because what we want is to the right of this value on the normal distribution graph. But the z-score actually only gives us to the left. So it's going to be 1 minus what the table can give us, which is z less than negative 0.36. Okay, so that should be pretty familiar. Now, I'm not going to bring out the z-score table, but hopefully you can look it up on your own. So if I'm looking up negative 0.36 for z-score, that should give me a probability of 0.3594. Okay, and if I subtract that from 1, I get approximately 0.64. Okay, and that tells us, therefore, the probability I got too many L's there, but it doesn't matter. Probability of at least a 9% return is 64%. So, okay, so let's try another question here. So same data, this time they're saying that the annual return will be negative, which means you're losing money. Okay, so what does that mean? Well, negative means you're looking for the probability that x is less than 0. So, same thing as before. We want to change that probability from looking at the random variable x to looking at a z-score. So I'm going to change the x to a z, keep the sign the same, and then we're going to go over here and we're going to calculate the z-score for an x value of 0. So the only thing that's different from this formula is I replace the 9 with a 0 on the top. Everything else is the same. 12.435 over 9.49. And that gives us a value of z equal negative 1.31. Okay, so I replace that 0, which is the x, random variable x value, to a z-score, equivalent z-score, negative 1.31. And this time you can see z is less than, means we just need to look up the table. We've got it to the left of the value, and that's what the table gives us. So when we look that up on the table, we get 0.0951, which tells us, therefore, there's a 9.5% chance or probability of a negative return. Okay, so hopefully that makes sense. We basically took this sample of investment returns, which we were told is normally distributed. We calculated the mean and the standard deviation using the applicable formulas. This time we used the speedy version that I introduced last lesson. Then once we had these, we could basically do the same type of questions we had from the previous lesson, where we're looking for the probability of the random variable being greater than or less than or between two values by using the z-score table. Okay. So there's one more question on this. So let me zoom in a little bit. It says, out of the next 10 years, how many years should Aaron expect to show returns greater than 6%? Okay, what assumptions are necessary to answer this question? Okay, so I'm going to start off this question just pretending it was a question that what's the probability that a single return is has a return greater than 6%. So what I'm looking for here is probability x is greater than 6. Okay, and we're going to change this from a probability of the random variable x to a probability of a z-score. But we need to, first of all, we need to convert that value of x into a z-score. So we'll do that over here. So hopefully you remember the formula. It's x minus x bar over s. So that would be 6 minus 12.435 over 9.49. And hopefully you're noticing every time I do this calculation for this sample of data, the only thing I'm changing for the z-score is the actual score I'm trying to convert, which is the number on the left at the top. And that is equal to, negative 0.679. So plug that in over here. Okay, now this time we want the probability z is greater than a value, and remember the table gives us the probability it's less than a value, so we have to do the old 1 minus trick. So 1 minus probability z is less than that value. And hopefully you remember the reason why this works, because basically the probability that of z being less than the value combined with the probability that z is greater than that value is always 100%. So that's equal to 1. So if we already know one side, we can just do 1 minus to get the other side. That's exactly what we're doing here. So if we do the lookup for that z-score, we get a nice value of 0.25, which gives us a total final answer of 0.75. So what that tells us, for a single return, the probability of a return greater than 6% is 75%. So that's not what the question said. It said out of the next 10 years, how many years should Aaron expect to show returns greater than 6%? So we basically assume that every year there's a 75% chance of that return being more than 6%. So in order to calculate the number of returns that are greater than 6%, that's just equal to the probability of 1 year. So in this case, we want to know 10 years, so it's going to be 10 times the probability of 1 year, which is 7.5. So that tells us that for 10 years, now you could either say 7.5 returns, or you could just say 7 to 8 returns. That would be totally acceptable. 7.5 returns are expected to have a return of 6% or higher. Yeah, so that answers the question, but there's kind of a follow-up. It says, what assumptions are necessary to answer this question? And this assumption would be true for any prediction. If you're trying to predict the future based on what you know from the past, you kind of have to assume that the future will look a lot like the past. So for us, we would be assuming returns are similar to the previous 20 years, or whatever years we were looking at. Okay, now that's nothing special for this specific question, but again, we're looking for the prediction for the future, so we have to assume that the future behaves the same way as the past. And that's not always going to be true, but we made our assumptions quite clear here. So, okay. All right, the second example, which is a multi-part question, is working with the continuity correction, where we're actually trying to look at a discrete distribution that has normal distribution and test for specific integer values. And we talked about that at the beginning of the lesson. So let's see this in action. Okay, so hopefully you don't get too hungry reading this. A company produces boxes of candy-coated chocolate pieces. The number of pieces in each box is assumed to be normally distributed, with a mean of 48 pieces and a standard deviation of 4.3 pieces. So they've already told us right up front that this will be a normal distribution. It's given us the mean and the standard deviation. We didn't have to calculate it ourselves like we did in the last example. Okay, quality control will reject any box with fewer than 44 pieces. Boxes with 55 or more pieces will result in excess costs to the company. Okay, so the first question is, what's the probability that a box selected at random contains exactly 50 pieces? Okay, so we know the mean is 48, so 50 is, a couple extra pieces. And what's the probability that you'll get a box with 50 pieces? This is what we're trying to find here. So, just like all other probability distribution questions, we have a random discrete variable here. And this we're looking at, and it'll be the same for all the other questions, so I'll just do it once, is the number of chocolate pieces in a box. Okay, very important to declare the variable before we use it right here. So, if I'm looking at 50 pieces exactly, we've already talked about how I can't do this. I can't say probability x equals 50, okay, like we could with, say, a binomial distribution. This will not work with a continuous probability distribution, but the way we fix that is that we go plus or minus 0.5 on both sides to make it a continuous probability distribution. So I'm not even going to put that there, but I will say what we want is the probability that the box contains between 49.5 and 50.5 pieces. So that's what I'll write here. Now, you and I both know there's no chance that a box will contain 49.5 or 49.6 or 49.78 pieces. It'll contain possibly 49 pieces, possibly 50, possibly 51. But in order for this to work on the normal distribution, we have to kind of turn it into a continuous distribution, and that's how we do it here. Okay, so the rest of it is pretty much the same as everything else we've looked at. I have to convert this probability of the random variable x being a certain value to the probability of the z-score being a certain value. So I have to convert both of these into z-scores. So so this time I have to do two of them. So z1 will be the first one. And I'm going to go right to the formula. It's already given us the mean of 48. So it's going to be 49.5 minus 48. And standard deviation of 4.3. And that turns into 0.35. Okay, and that makes sense. You know it should be positive because it's above the mean, but it's not a full standard deviation above. It's only 1.5, so it's that seems quite correct. Then we'll do the second z-score for the 50.5. So all we do is we change the 49.5 into a 50.5. The rest of it stays the same, and we get 0.58. Okay, and now we go back here and we just change this into a z-score probability. We have an upper and a lower end, but we've done those before. So the 49.5 was the top one, so that's a 0.35, and the 50.5 has a z-score of 0.58. Okay, so we've turned it into a z-score problem, but we've got this double-sided or double-ended probability, and we know how to change this. We've done this before. So I want to start with this, everything to the left or less than 0.58. Probably z is less than 0.58. But we want to remove everything to the left of 0.35. So that would be probability z is less than 0.35. Okay, and when we look these values up on our z-score table, we get 0.7190, and we subtract this z-score, which the probability for that is 0.6368, and that works out to 0.082. Okay, so that tells us there's an 8.2% probability that the z-score is between these two values, which means that the number of chocolate pieces are between these two values. So this is our first look at continuity correction. So this tells us the probability, there is an 8.2% probability that a box will contain exactly 50 pieces. Now, if you look back at this, you'd say, no, isn't it calculating the probability contains between 49.5 and 50.5 pieces? Well, yes, that's the way we did it, but this is our continuity correction. There's no, we basically go plus or minus 0.5 of that individual discrete value that we're looking for. Okay, so that's our first real continuity correction question. So let's try maybe a couple more. What percent of the population will be rejected by quality control as containing too few pieces? So if you go back to the definition of what too few meant. Fewer than 44 pieces is too few. So what we're really looking for is less than 44, but we have to do a little correction here. So instead of 44, we're actually looking at, so 44 is fine, 44.5 would be fine, even though it can't happen. Anything down to 43.5 would be considered good. So what we're looking for is less than 43.5 for your x value. So probability x is less than 43.5 would give us the probability of fewer than 44 pieces in a box. So this one's a little easier. There's only one lookup, only one z-score to convert. So let's do that here. So I'm going to convert 43.5. So I subtract 48, divide by 4.3, standard deviation. And we get negative 1.05. So this probability statement changes into a probability of a z-score being negative 1.05. Then we do our table lookup and we see the probability is 0.147 for that z-score. So our word answer, therefore, 14.7% of production will be rejected for too few pieces. Okay, so hopefully you're getting the hang of this. Have to convert the actual integer values into a range of plus or minus 0.5 around those values we really want. Okay, so let's finish this off. I have a couple more questions related to these chocolates, which is making me quite hungry. Okay, so the next question. Each filling machine produces 130,000 boxes per shift. How many of these will lie within the acceptable range? Okay, well, if I look back at what's acceptable, so quality control will reject any box with fewer than 44. So basically minimum 44 pieces, but 55 or more pieces is bad. It's too many, we're losing money. So the boxes have to be between 44 and 54 because, so I'm just going to write that down so I don't forget. So that's acceptable because 55 chocolates in a box is going to cause us to lose money, and 43 or less means we're ripping off our customers with too few chocolates. So this is the sweet spot here, 44 to 54. Anything outside of that would be unacceptable. So now I have to do my continuity correction because I can't say what's the probability between 44 and 54. Even though it's a range of values, I still have to do the correction on both sides. So basically now what's acceptable in the continuity distribution is 43.5 up to, and go 1.5 higher than that, 54.5. And you have to be careful because it's quite easy to to make a mistake and put 44.5 here or 53.5 here. Remember, you're going 0.5 to the outside of what you really want. Okay, again, we have to convert these random discrete values into a converted z-score. So the first z-score value we actually already did on the previous question. So I'll just save myself some time. I'll write the number here from before. The second one, the 54.5, we haven't done that one before. So that is going to be 54.5 minus 48 over 4.3. That's equal to 1.51. Okay, so now we can replace these two z-scores for these two values for x. So that's a negative 1.05 less than z, and the upper end will be 1.51. Okay, so now again, since this is like a double-ended range of values, we have to convert that into the subtraction of two probabilities. So it's always a probability of the first one minus the probability of the lower one. Sorry, probability of the higher one minus the probability of the lower one. So probability z is less than 1.51 minus the probability that z is less than negative 1.05. And we look those up in our z-score table. 1.51 gives us 0.935, sorry, 345. Subtract that probability is 0.1469. That is equal to 0.788. So what does this actually give us? This is the probability that a given box is within the acceptable range of number of chocolates. And if that was the question, we could give that probability right here. Question was, if you're producing 130,000 boxes, how many of those 130,000 will be acceptable? Well, if one box has a probability of 78.8% being accepted, then we just multiply these two together to get the number of acceptable boxes. So 0.788 times 130,000. And if we do the math, it's 102,000. So 102,000 boxes will be in the acceptable range. Okay. And this is just kind of a logic thinking type question. So if you own this company, what conclusions might you reach about your current production process? So your job is to make sure your company is profitable and customers love you. But we saw some things here that could be a little alarming. The first one was that we saw that 21% of products boxes will be rejected. That's very, very high. So that would be the first thing I make a note of. Too many rejects. 21% of all your production. Okay, and what might you do about that? Well, this seems to be a problem with the assembly line or the production line that, I mean, modern technologies should be able to make sure there's exactly 50 chocolates per box, which is what you're hoping for. So the fact that you're getting a lot of boxes with fewer than 44 and more than 54, that's not acceptable. So probably what I would do is study the production line for faults. could be a very simple thing. Maybe one of the lines is causing all the problems and you just need to fix it. But maybe it's the whole thing. Maybe your equipment's too old. Maybe you should buy new equipment for the production line. But only if necessary. Okay, so that's the lesson. I've got some homework questions there for you to try as usual. But fairly short lesson, but it shows you the main thing we worked on was the continuity correction, so that you could actually use find the probabilities of certain discrete values. If you had a discrete normal distribution, you could actually use it for very specific values. You saw the first question we did, we were looking at probability the box had exactly 50. We're able to do that now with this correction. And that carries over into other calculations of a range of values. So I know I told you at the very beginning of this unit that you couldn't do that, but I told a little white lie, and I apologize for that, but this is how we get around that. The next lesson we're going to be looking at, we're going to take a trip down memory lane. We're going to look at the binomial distribution and how we can actually estimate the binomial distribution using normal distribution. So that should be interesting, and that should just about wrap up the unit. Okay, so hopefully you enjoyed the lesson, and we'll see you on the next lesson. Have a good day.